Hello, everyone. I'm Maryam Forouhari, and I'm going to talk about distance measurement system today. Well, every year, thousands of car accidents happen. Sometimes because of the drivers that they don't see, but in autonomous vehicles, sometimes that's because of the distance miscalculation. Sometimes the vehicle can't calculate and estimate the distance very precisely. So it can cause late brake and a collision. So it can cause a disaster. Well, actually, to avoid this, we have to have a precise measurement system. That's the reason that we need this, and it's a safety requirement. Well, let's look at the human body. Let's look at the human body. Have you ever thought what would have happened if we had one eye? Actually, two eyes is for estimating the distance. Stereo vision is inspired by human vision. And by this, we can find and estimate the distance. It's a passive device without laser, and it's cost-effective and environmental friendly. It consists of two cameras in one line, and with this, we can find the distance. But there are some challenges. The most important and the first challenge is camera calibration. Well, usually the values in the datasheet of cameras are not very precise, and cameras are imperfect. Well, with this, we can find the precise specifications of cameras. And then we have to find the exact location of the object in the images, in left and right image. And finally, we can find the accurate distance. Well, to overcome these challenges, we can do some steps. The first one is we have to calibrate each camera and then do the stereo calibration. With this, we can find the precise specification of camera to have a precise measurement system. And then we use object detection. Using deep learning algorithms like YOLO, we can detect the objects like, for example, bicycle or, for example, cars and pedestrian. And then using image matching algorithms, we can match the image in left and right. In left and right cameras. And this can be done with a Siamese network. And finally, we can find the distance with geometry and triangulation formulas. Here you can see in the image, I don't know if you have tried this, you can try now. You can look your finger and close your left eye, and then look at your finger with your right eye, and then close your right eye and look at your finger with your left eye. What will you see? You can see a shift between the image, and that's the disparity. That's the horizontal displacement in the image, in the left image and right image. Well, by using this disparity, we can find the distance. Well, we talked about the barriers and challenges, which, for example, is imperfect field of view, can be overcome by stereo rectification and calibration. And to reduce the noise and misalignment, we can use the robust object detection and we can use the robust object detection. Well, as a result, the mean measurement error was 0.4%. This accuracy is promising for vision-based systems, which are considering low cost, passive sensing, and that's real time. It's very important. Here in the image, you can see Actually, that's me wearing a mask because it was during the pandemic. If you click on the image, you can find the distance, which is written here in meters. In conclusion, we can have, after overcoming the challenges, we can have a precise system which is very safe for vehicles, and it's a scalable vision system, and with a lower carbon footprint, and it's environmental friendly. Thank you for your attention.
Thank you very much. So I'm waiting for your question.
Thanks for this presentation. Can you tell me how does disparity relate to depth in your system?
Okay, the disparity. Here you can see the relation between distance and disparity. Distance is proportional to 1 over disparity. Disparity, actually, as I said, is the horizontal displacement in the left image and right image of two cameras. Here in the image, you can see X2 is the disparity. With finding this for each object, we can have a disparity map. And with the disparity map and the precise specifications of camera that is calculated using camera calibration, we can have a depth map, and actually with that we can find the distance.
So you are saying there is an error of 0.4?
Yeah, that's usually for closer distance. As you know, if we find if we go to the further distance, here actually I'm written, for further distance, this shift is smaller, and there would be more error. But the error percent, which was here, was for the distance less than 40 meters.
Okay, but I would have expected 0.004 instead of 0.4.
Yeah, but actually it's common in these systems. For example, if you compare this with the other distance measurement systems, with stereo vision, LiDAR is more accurate, but it's more expensive. But with this system, which is with low cost, and we can, that's acceptable.
And I was wondering if there are any constraints in terms of responsiveness or something like this, because you say you are running YOLO and things like this. And so is it in terms of seconds, milliseconds, or?
You mean at the time that it detects?
Yeah.
It was very real time. No, because we at that time we used a YOLO version 5. That's very light, and it doesn't take so much long to detect an object. And
what do you call
real.
not very much? Is it milliseconds or?
Yeah, it was millisecond.
Okay. Okay. No. Why you are choosing?
Thank you for your presentation. Why did you choose stereo vision instead of LiDAR for distance measurement?
Yeah, well, LiDAR is more accurate, but it's expensive yet, and with actually it's a complex maintenance, and well, it consumes a high level of energy. But stereo vision consumes less energy, and that needs much power in LiDAR. So this is good if we don't want, for the systems that we don't want to expend so much money with good precision and accuracy.
Okay, thank you. So thanks again for your presentation.